Thanks. So I hope you had fun. So now I get to have fun reading all these, so that should be great. So I'm actually looking forward to reading them. Just it's just going to take me a while to get through. So I'll try and give some. So if things go really well, I'll try and have them maybe so you can pick them up with comments at the poster session. But no promises. So that's my goal for trying to get them done. So hopefully you'll be able to get a sense of your grade, so at that point. So just look at the schedule. There are a few things coming up to mention. One is there's a poster outline due on Wednesday. So this deadline seems like it's a little bit early. It's a full week in advance of the poster session. It's only in 2 days. You've probably just been working on your final reports. Well, so the reason we have that there is because the department has graciously agreed to print posters for you if you make them, but it takes them a while to do it, so they don't want to get them all at the last minute. So there's a deadline for sending. So let's look at the project PDF. Okay, so I haven't completely confirmed, but I think the poster session will be in this room. So I'll talk about some details of that soon. But if you get the posters ready to be printed and you have them as a single PDF and it's 2 feet by 3 feet, which is not huge, then you can send it to Chris Coleman at the address there with a specific thing in the title and so forth, and your name, .pdf as the name of the file. If you do that all correctly, the department will print it for you in color. So then you don't have to worry about that, and we'll probably have the posters all here, or maybe somewhere in the front office of the School of Computing. So if you want to do that, please, I want you to send me a draft by at least Wednesday, or you can talk to me and show me. A few people have already done that. It just takes a few minutes, just so I prove to make sure you're on the right track. I don't want you kind of printing something and then going back and ask me about it and then try and see if you can change it, because that's just going to be a mess. Okay, so I think it's worth spending a little bit of time to outline what I want in the posters, and then I'll actually show you some examples from the past year. So it should be pretty similar to what was in your project, but with a lot less text, more emphasis on the pictures. And so the target audience here are going to be other people in the class, and me. And I may actually invite some people from some local companies who are doing data analysis around to come look at the posters as well. So hopefully you'll get a chance to kind of to show off some of the work you're doing and get some other interesting feedback. So you should definitely it should be upfront and clear what the problem is that you worked on, and also what are the key ideas that's new that you're bringing to this, right? So other people work on the same problem. The ideas are your approach towards this problem and why it's different. And so then say specifically what things from class was used in the project, right? So if you have some main idea, you want to show how you connected to class, and then what you learned from it, right? So what's new, what's the discussion out? Okay. So then a couple of notes on types of posters. I've seen lots of posters, and there are generally 2 types. One is very common in like biological sciences, where they'll make these really big posters. They'll go to a conference and they'll leave them on the wall for like 3 days, and they won't necessarily be there in front, and they'll have lots of text on them. And you can go there and you can read kind of a short version of the paper right off the poster, but you have to kind of get close and squint and read all this stuff. So the other type is where you're meant to be standing next to the poster explaining someone what you did, and then you want some visual aids to help explain them. If you could draw pictures, you would draw the same pictures that you're using on your poster. Or if you have images that you have, you would use those same images on the poster. So this should be type B. This should not be your whole paper is embedded in the poster. It should be, should be this, not the whole paper. It should be the second type where you're using and building some visual aids to help explain the concept. So let me try and show some. So let me try and show a few examples here. So these are some posters from the last couple of instances of the class. So this one was on stock price correlation, and so you can see very well what the topic is, and and they have this twist section where it explains what they did different, and then they have some examples. So this one did not have a lot of kind of pictures to show, but they showed some examples of text from the clusters they found. The thing I don't like about this poster as much is that it's got a whole lot of text, and you can't read it from where you're sitting right now, right? Most people who are looking at your poster will be kind of relative distance to scale the same size away, and they will have trouble reading this text. So don't make the text this small. Right, so this one is about mining patterns from some car simulations, and it's got the nice title, and you see who it is. Oh, on your poster, make sure it has a title and your name on it. Other people will be going around assigned to your poster. They need to be able to find it. If they can't find it, that's not as good. So, and you can see it's got lots of nice visuals trying to show the results of these k-mean clusterings and the results of matching some curves using some dynamic time warping thing and some visuals to illustrate what's going on here. So I thought the font's a little bit bigger here. It's more in the bullets, easier to follow quickly if you're talking through this poster. It's also, because it has the bullets, it's got easy reminders of what you want to tell someone about as they're coming by. So this is one on time series clustering, and it's got described what the key ideas here. It's a little bit more in text. I would have rather this had more kind of bullets, the main idea, but that's okay. And it shows kind of pictures of what the visual mapping of what the data looks like, and then some pictures try and show what the results are. Kind of different, relations to class and the main techniques and the main conclusion. So this is a good, kind of layout of what you think the poster might be. So this one you're gonna like. This is by someone in the room. Reza. So this was Reza's poster from 2 years ago. Not to put it, I guess to put him on the spot. What?
Last year.
From last year, yeah. So it was on finding clusterings, multiple clusterings in graphs, so you get kind of a visual picture of what you think of with the clusterings in graphs. And this was another smaller example to kind of illustrate the key concept. So you could bring it out from this example. And then various kind of experimental results and tables that, and this really nicely shows the results. And if you're designing it, you break it up into these chunks. This kind of helps you kind of move through the poster and understand, kind of modularly break it down. So this is a useful kind of techniques to have. Let's see what else we have. All right. So this was this is a poster where this data set they got was kind of correlated. They had some data for each of the states in the U.S. based on the U.S. Census, and they were trying to kind of do some clustering on this data, and they were able to kind of do a lot of nice visual mappings onto the map of the U.S., and this really kind of illustrated what was going on in a nice way. So this was, I thought, a really nice, visually appealing poster where they kind of were able to kind of quickly throw up data and take the concept across really quickly. And then one more I'll show you. Right, so this was on property value, and so again they try to get some visual mapping of their data into some representation where they could show it. And you can't see too well on the projector, but they had data around, I think this was Baltimore, but it was around Baltimore. It didn't actually include Baltimore here, and they kind of really showed this visually really well. And they had some different kind of, this was more, I would say, probably a little bit more pictures were separated from the text a little bit too much. Should be really, the label should be closer to it instead of a bunch of text down below. But this was a really cool poster. It had a lot of nice visual things. So there are also other posters that people have made where they're just kind of some slides where they kind of made like a PowerPoint presentation and posted those up. And those can also be effective. They're probably not going to be as visually appealing. So one more thing in the part of the poster is people are going to go around and have to be assigned to talk to your poster, roughly 2 people per the number of people on your project. And so they'll have to do that, but also you'll supposed to go around and choose the best posters you think from the class. And the winners that's voted by all of you, you can't vote for your own, will be awarded extra bonus points, right, towards your grade. So, and in the past, the kind of posters that have been a little bit more clever with the visual layout have gotten more votes towards this. I don't remember if this poster was the most popular one in the class, but this one and I think the previous one were at least ones that were in the, or at least in the running. So kind of spending some time on it, the layout will really, be to your advantage there. So some people would rather focus on this aspect, and if you can do a really visually appealing and kind of where you're still conveying the data analysis techniques you did well, your class will be able to vote, towards that. So it's so hopefully it's gonna be a lot of fun. It's gonna be like a really kind of like high energy 2 hours. So I hope everyone gets a lot out of it. Okay, so let me see if anything else I want to say about this. Yes, I talked about these 2 techniques. So in the poster session, there'll be 3 types of people going around to see your posters. There'll be the 2 people who are assigned, or 2 people per person who are assigned to your poster. There'll also be the other people voting for it, and then I'm going to have to go around to all the posters, and I'll try and do this all in the class. This will mean I'll get roughly 2 to 3 minutes per poster. So you should be prepared to give me a 2-minute overview of the content in your poster. And then I will try and ask a few questions depending on how much time I have. So be prepared to give me a very quick 2-minute overview of everything you've done. And this takes practice to do well, so if I haven't come to your poster yet, practice with other people as they come by, and maybe even practice a few times ahead of time. As you're designing a poster, I find it's very useful to actually practice talking through how you would give a presentation. And it'll say, which things did you point to when you were kind of talking through it to yourself? those are things that you want to make sure they're on there. Things you didn't use, maybe you can take those off the poster. Things you wish you could have pointed to, maybe you should add those on, just kind of as you're going through the design. So kind of think about giving a 2-minute presentation. Okay. So one last thing about the poster session. So it'll be the last day of class in here. I need to figure out how long we have this room. I'd be in favor of extending the time by a little bit. Now, I'd only need you to be here from 5:15 to say 6:35 or so, but we may try and start from like 5 to 7. That way it'll give me a little bit longer per poster, so I can get through all of them. So I'll try and look at how long I can actually book this room on that day, and I'll try and get through. If you can't get here till 5:15 or you have to leave 6:35 or something like that, that should be fine. But hopefully most of you can kind of extend that a little bit, so we have, it should be a lot of fun to see all your classmates' posters anyway. So. Okay, so then the last administrative thing is the last homework assignment, and I just posted this over the weekend, and this will be, it's due April 29th. So I will try and make sure I get all the other grades out posted by then, so then you can decide if you want to do this extra assignment. This last assignment, as I said, is going to be optional. So if you don't, your homework assignments will be worth half of your grade in the class. And that half will be averaged with the parts of the project. If you do this, I will average this one into your grade, okay? But it'll be worth 10 points, but you can get up to 20 points, okay? So you can make up some by doing this extra assignment. So the extra 10 points are like bonus questions, but they're not going to be as challenging as a lot of the ones earlier, which were kind of meant to be very hard. These are meant to be, about as hard as a regular assignment question. So right now, the first 5 assignments had 90 points total, and I'll take those points and divide them by 90 to give your percentage for that part of the grade. If you do this, I'll divide through by 100, but you can get 20 points. Okay, so if you do the full assignment, it can really help your grade. So it'll basically be walking through these different ways of calculating the PageRank vector, or just kind of converging this Markov chain and then doing it, and then the first part of the bonus is doing it with the taxation, so you're approximating the PageRank vector, and then the last part will be on the last lecture of the class, which will be on graph sparsification, and you'll just be implementing one of the techniques for this. So if you go on Canvas now, I believe this is the case. I don't have the same view of the data as you, but I think it'll average your homework grades out of your current assignments, and so that will be a representation of the percentage you're getting for the homeworks. So you can pre-calculate that, and if I do this, I will just add in the points you get here and divide through by 10, so you could get 20 out of 10 points. So any questions about this? Okay. All right, so let's look at the schedule where we are. We talked about MapReduce on Wednesday, if you could bear the cold and the shade. And the air conditioning units outside. So today I'll talk about how they kind of do PageRank using MapReduce, or how to think about this. Okay. So as a kind of another example of how to use MapReduce. It'll be more complicated than the simple ones we went through on Wednesday. And then the last 2 lectures will be kind of some cool properties about graphs, which are kind of different, kind of related to kind of, they'll be kind of related to other concepts we did in class, but the techniques for thinking about graphs will be different than either kind of the spectral techniques which kind of include the PageRank. So other ways of detecting communities or other properties of graphs, and how do you take a large graph and reduce it to a smaller one that kind of maintains some of the properties. So those would be the last two features. All right. Okay, so all right. All right, so what I'll talk about is how do you do PageRank using MapReduce, and I'll start by quickly reviewing so MapReduce. I'll quickly review PageRank, and then we'll kind of walk through some different ways of doing this. So first MapReduce. So it's got these three main stages. So it's got this map stage, where it takes data that's stored in some way, distributed as these key value pairs. And so for each key value pair, it's going to generate some set of other these other key value pairs. Okay, so you can think of all of your data as somehow abstractly stored as these key value pairs, which is a very general representation without a lot of structure. The key is just some identifier generally, and the value can store a lot of stuff, such as like an entire document, right? So this could be the text for an entire document, all the HTML of a web page, including all the links. Maybe it's just the links of the web page. Maybe this is a log from some big log file. And then the map step converts this into a set of these key value pairs. And these key value pairs will be useful because you're going to use these to kind of bring the things that are stored in this distributed way all into the same machine so you can do some more relevant analysis on it. Right, so the second step is the shuffle step. And what that does is it brings from across all of the data you've processed, and this is some very wide data, all of the key value pairs with the same key onto the same machine, basically. So all of these key value pairs with k equals to key, then we move these all into one machine, and you can think of having some key and then all of these values. Okay, so it magically does this. This is done, this is from the output of the map, the shuffle phase does this, and then, but you don't specify this. This is a built-in function of MapReduce. And then the third step is to reduce. And this takes as input one of these keys and all of its values and does some computation. Okay, so this takes in some key and all of the associated values. And it outputs, again, in the most general sense, one key value pair, or it could be again, I think it could be a set of these key value pairs. So it could be key prime and value prime as the output. Okay, so this is kind of a general pattern. All you have to specify is this mapping step, which is generally just scanning over each of this data stored in the value, and you're kind of converting it into this format. It automatically does the shuffle step for you. This is done in parallel across many machines, and then you have to write this reduce step, which now you have all the data that you wanted all in one place based on this key, and then you get all of these values and you have all the associated values. Now you can compute something as an output key value pair. Okay? And then there was this other step that was in between here. So this is all done on one machine. This is done in parallel by the system. This is all done on one machine. You can have another step that's called the combiner that works on the same machine as the mapper, and it can take all of the key value pairs with the same key on one mapper and consolidate them in some way. So it's doing something like the reduce step, but before this parallelization step. Okay, so this will take all of the key and so usually this will consolidate into one thing with the same key and one value that is a combination of all these values. So it does this before it sends it off this machine, and this can reduce the amount of communication, the amount of data that the process has to send here. Okay. And this will be useful to keep in mind as we're talking about doing PageRank. This was useful when we were talking about this very simple problem of doing word count, where if these values were these documents, we wanted to count how many times each word existed. Well then, because if you have 100 or 1,000 machines and the word the occurs 7% of the time, then the key associated with the word the would overload one of these machines. So if we can bind them first, before we sent them, this machine would not get as overloaded as it has to use the word the. It may not completely solve the problem, but it's going to reduce the load a lot. Okay. So that was MapReduce. Now we'll quickly review PageRank, and I'm going to use a small example graph here. Okay, where I have these 4 nodes, and the graph has output. So you can think of each of these nodes as a web page, and if it links to other web pages, then we draw an arrow. So A links to A, B. If A links to B, C, and D, I draw an arrow, and I say it has a 1/3 chance of going to each of these pages. Okay, and then B will go to A and D. This only goes to 2 things. It has a 1/2 chance of each of these. C is always going to go to B. So this has a 1, probably 1 going there. And D, half the time, half the time goes back to B, and half the time it goes to C. And that means I can write this as this probability transition matrix, saying if I'm a random web surfer at page C, I always go to B. If I'm at B, half the time I will go to D, half the time I will go to A, and that looks like this matrix here. We'll call this P. So this looks like 0, 1/3, 1/3, 1/3. This column represents A. I never go to my own web page, but 1/3 of the time I go to each of these other web pages. If I'm in for node B, 1/2, 0, 0, 1/2, 0, 1, 0, 0, and 0, 1/2, 0. Okay? And so kind of this models if you're randomly surfing around. And what we want is this transition. If I'm at one state described by Qi, describes is a vector of length 4. It says a probability distribution over which state I'm at. I want to say where I am the next time. And the simple way of doing it is just doing the matrix P times the old state. So I'm at this distribution, I'm going to transition based on this matrix. I wind up at this new state. But PageRank is going to instead say that, and I'm not always going to do this. I do this some beta fraction of the time, where beta equals, say like 0.9 or 0.85 are common values. And then, so 90% of the time I do this just as I described, and 10% of the time, so 1 minus beta, then I'm going to jump to a random web page. So this says I can go to any web page at random here. So if there were n different web pages, these would each be one at random. Okay, and then if I do this step a bunch of times, eventually I will converge to, and we said that this satisfies these properties of ergodicity needed. This will converge to a vector Q star, and this is the PageRank vector. And so the higher the value in each spot, the more important each of the web pages is. Okay. So after this converge. And maybe this will converge in many cases after, like, do 50 steps, this will often be enough. As long as you don't start with something really, really strange for the initial condition Q0. Okay. So why do we want to use, so in the homework that hopefully you'll choose to do, you will see how to do this on a very small graph example, slightly larger than this one. And you can just do it on using MATLAB. If you had a really big graph, let's say if you're Google, you want to do this on the web graph. Why do we want to use MapReduce instead of just using Map?
So that you can do parallelly. You can, because this problem kind of looks like you can solve it in parallel.
So what? So it's true. We do want to do it in parallel because we can do the computation. We can spread out the computation across many different machines. But it's not clear how to do this in parallel, actually. At least, so maybe it's clear to you how to do it, but that's one thing we'll talk about. And computation is not the only reason that you want to do it in parallel. So who in class tried to run some algorithms for their project where it just wouldn't finish, right? Where it was just taking too long, right? So sometimes this is because of the computational thing you have to wait for. Sometimes because the processing will use up a lot of memory. If you try and load a really big matrix into MATLAB, it's going to say it's now going to fit your memory, and so computation is going to take really too long. You keep trying to pull stuff from disk, and this is going to take more than actual computation, right? So the memory constraint is really an issue here. Okay, so you're storing the entire web on a computer. You can't do that on a single computer. Okay, so how many web pages currently are there on the web? So I looked this up on the internet this afternoon. So I don't know how accurate that is, but they said how many web pages that if you went to the address, it would actually resolve to something there. So not something that automatically redirects. So does anyone have any guess?
100 billion?
100 billion.
Bazillion.
Keep bazillion. Five. Okay, so it's actually not that big, as at least according to the internet. So it's slightly under a billion. So it's like 950 million. And it's growing. By the end of 2014, it should be $1 billion. It actually went down a little bit last year or something weird. Okay, so but let's say there's roughly 1 billion web pages that you want to index. And these numbers are fishy for a number of reasons. Kind of there's dark matter. There's something known as the deep web, which is you can only get to if you get through a search like through Amazon. It's hard to directly get to some of these web pages, or you can only get to it if you have some password to get to it. So it's not clear what this means. But let's say Google is trying to index 1 billion of these web pages. So that means that just the size of this vector QI has 1 billion entries. Okay? And so, and these entries are not just storing like a bit either. Right? The end result is this PageRank vector, and we know that we have the property that the sum over this sum is equal to 1. Okay, so that means to store anything useful in here, I have to have a lot of precision. Right? Because basically the average web page will have value 1 over 1 billion. Okay, so in order to store this, I need to have a lot of precision here. And there's a pretty big variance in between the values of these. Some random web page is going to have a really much smaller than 1 over 1 billion, but a popular web page, like the homepage of Wikipedia or something, would have a considerably much higher value. Maybe even like 1 over 1,000, maybe the top things for PageRank. So there's a big difference in the values here. So you need to store this with a fair amount of precision. And you have 1 billion entries here. Okay. So even storing this on one machine in memory is going to be tricky. You could probably so maybe you could store it, but you don't want to have to process all these things on just one machine as well. We also have to store this